inverter. And we said now I will have an NMOS to act as the pull-up, as the connection between VDD and the out, and another NMOS to act as the regular pull-down to which the input signal is arriving. And we said that in order to solve for VOH, I set Vin for the main NMOS to be less than Vt. Okay, so this is my device. If I set Vn to be equal to 0, for example here, and if I set Vn equals to 0, then the device is going to be off. And here I will have VOH at the output, and for this transistor, it will always be in saturation, and it will really continue to charge the output until it hits the almost being off. يعني هيكون saturated with the current equals 0, and it will turn off at VGS equals to 0 minus VT at VOV equal to 0. Okay, so we said last time that if I have the NMOS charging a node, it cannot pull it up strongly all the way to VDD. It will pull it up to either VDD minus VT if the input gate is VDD as well. Hello. For the same circuit, I can really find the other points in a similar fashion. So for the same circuit that I have here, I can sorry بس لأن هيدا شوي and the loading is for the same circuit that I have here, I can also find the other points. يعني I can solve for VOL and I can solve for VM. Okay, so for example, to solve for VOL for this circuit, what I can do is, I'm just trying to get an empty slide, but I'm having trouble with this. Okay, so what I can do is I can set the input now to VOH. Okay, and if I set the input now to be VOH, I will order them later, it's okay. So if I have my transistor up here and 2, and this is VDD, and then I have my transistor N1 here, and I set this now to VDD minus VT, and I try to check what VOL is. Then for transistor N2 in a similar fashion, and for transistor N1, I will look for the operating regions. So for this guy, I will have VGS minus VT, and I will have VDS as well, and I will try to determine the region. And for N1, I will have VGS minus VT, and I will have VDS. So for transistor N1, VDS is VOL, and VGS minus VT, تبقوا إنه this is VN. So it will be equal to Vn minus Vt, which is VDD minus Vt minus Vt. And VOL is the VOL that I'm trying to solve for. Hopefully VDD is large enough and VOL is small, close to 0, maybe 0.1. So the region, whenever we solve for VOL, is typically the linear region, and this is small. The minimum is VDS. Okay, whereas for this transistor, if this delta at the output here is small, okay, so if my delta here is small, then between VDD and VO, the voltage here will be large. Yani let us look at VDS. VDS, this is D and this is S. So VDS is going to be equal to VDD minus VOL. So it's going to be large. Okay, for any other application. Now here what we have, it happens that the transistor is connected in a saturated fashion. So really it doesn't matter to me if it's small or large, because VGS minus VT is really VDD minus S is VOL minus VT, and the VDS is VDD minus VOL. So this is VDD minus VOL. If I am using only the long channel model, therefore I will have this in saturation, لأنه this is definitely greater than this, and I will be operating in saturation. And therefore, in order to solve for VOL, I will end up with some form of quadratic equation where I will rely on the fact that IN2 equals to IN1. What we can do, we may still be able to say that VOL is very small, so any quadratic terms can be dropped, and we can end up only with the linear terms in the equation. But we have to be careful here that this current, if I take it half K prime W by L VOV squared, this is going to have VOL in it, okay? And this one here is going to be K prime W by L times VDD minus 2VT times VOL minus VOL squared على 2. طبعا هيدا if I'm ignoring the other parameter, يعني 1 plus lambda effect, okay? This is the gist of it. Now, if I set Vin equal V out equal Vm, then this will be in saturation, and the top one N1 become saturation, N2 become saturation, and we can solve for the switching node. Okay? حدا عنده سؤال على solving for VOL؟ طيب هلا we're gonna jump into the okay, hopefully it will save it. Okay, now we're going to jump into, maybe I should close this. 1 second, bear with me. Okay, so data. Sorry. Okay, let's see. Okay, let's see. Okay. So now if we have if we look at the third type of inverters, so the third type of inverters was the, let me just delete all of this. Okay, was now what we call the linear enhancement mode, اللي هو هيدا third, the linear enhancement, which is this third circuit here. And the difference between this and the previous one is that this is an NMOS, okay? But instead of connecting the gate to VDD مثل ما كان عندنا هون, we connect it to a new supply called VGG, okay? And let us see what the implications of this are. Okay, so let us see what the implications of this are, and let us hear. I don't know what's happening here. Oh, it's in select mode. Okay, let me second. How can I do escape? Okay, no, it escaped, hopefully. Okay, so okay, so okay, so now if I have the same NMOS transistor, but I have this connected to VGG and this connected to VDD and the output, then based on the rule that we said, VO is going to be the minimum of VGG minus VT and VDD. And هذا maximum possible charging, صح? Charged value. So what do I set? If my objective is to hit VDD, what should I set VGG to? I want to maintain an output of VDD. So therefore, if exactly VGG is greater or equal to VDD plus VT, بصير ال VDD هو ال winner, and I will always charge the VDD to the output to VDD. Okay, so I can always charge the output to VDD. So this is what this circuit does. The circuit is really, now I have this is VGG, let us assume this is VDD plus 2VT, and this is VDD, and here I will have VN, and this is a ground, and this is my VO, this is transistor N2, this is transistor N1. Now what do we notice about the transistor N2? What is the special characteristics for transistor N2? If we look at its VGS minus VT and its VDS, هيدي ال VG is VDD plus 2VT, right? minus VO لأن الsource node is O minus VT لأن because of the minus VT. And VDS is what? It's VDD minus VO. Okay, so really VGS is VDD minus VO plus VT. Okay, so who is larger? مين أكبر? Who is the winner? Who is the minimum quantity? What region I am going to operate in? Pardon me. Right, so I'm going to operate in the linear region. ليش؟ لأنه now, so this is definitely BDS is the minimum, and I'm going to operate in the linear region. And this is why we call this linear enhancement MOSFET. Okay, يعني in this scenario we allow VO to reach VDD. We can have a VOH, okay, that reaches VDD, and the transistor is therefore going to operate in the linear region. okay. طيب بالنسبة لل VOL اثنيناتهم حيكونوا linear, so both will be on. As long as both transistors are on, this means that VOL will not reach 0. Is that clear? Okay, great. طيب حدا عنده سؤال على هيدا type of inverter?
But Professor, the very last idea you mentioned, as long as a certain condition holds, it will not reach 0. Can you please repeat?
Yes. So هلا if I want to look at this same circuit, and this circuit, if I want to look at it in the when I'm solving for VOL, so I have transistor N2. Okay, this is VDD plus 2VT, and this is VDD. Okay, this is VO, and I have my transistor N1. Okay, N2 عفوا. And let us assume that I have Vn equals to VDD اللي هو VOH, and I have VOL here, right? So in this scenario, N1 will be on, right? And probably in the linear, and this is VOL, this is small. N2 will still be in the linear region, and its gate is higher than the drain, right? So it will be on, right? So when I solve for VOL, what do I have? I will have IN2 equals to IN1, and both devices are on, right? When both devices are on, really I can think of them as some resistor Rn1 and some resistor Rn2. يعني أنا I have a current connecting me to VDD, and I have a current connecting me to ground. So the V output will not be able to reach pure 0. So VOL cannot become 0. It will be somewhere low between VDD and ground, but not perfect ground. Okay?
Okay.
So if both devices are on, then I cannot reach 0. Okay, thank you. طيب هلا we're gonna look at now we're gonna look at the last type, or before last type, okay, of the inverter. And this type, we will refer to it often as pseudo-NMOS, because later we will learn about logic gates that rely on this type of inverter. So هذا الانverter that we see here, the inverter that we see here is really the pseudo-NMOS, pardon me, the pseudo-NMOS inverter. Okay, so هيدا هون the last one معلش is the pseudo-NMOS inverter. Let's see what a pseudo-NMOS inverter is made of. So I have my pull-down device, okay, which is transistor N1, and the Vn is coming here, and this is the output voltage, and then I have my pull-up device, which is a PMOS, which is grounded, and this is connected to VDD. Hello. Why do we choose to use a PMOS here? Let us see. For the PMOS, when it is pulling up the voltage, Okay, where is the S of the PMOS? And this is the gate of the PMOS, right? So VSG of the PMOS is equal to VDD, and it's always greater than absolute value of VT, right? Independent of the what? The voltage, independent of VO. So this means I do not have any constraint to what VO is going to be, right? يعني VO can rise all the way to what? To VDD. Okay, without the device switching off. So a PMOS is a good pull-up. And this is why in the CMOS we put the PMOS up. Okay, now this means that I can build even other types of logic with it. But first let us look for this pseudo NMOS. And the name pseudo NMOS comes from the fact that this logic block here reduced to an inverter can become a NAND, can become an OR with only one PMOS pulling up, except when the pull-down network is evaluating. Okay, so for this pseudo NMOS inverter, let us say that I want to solve for VOH. So I will set Vn to be equal to 0, for example. This means that N1 will be off. Okay. And then if VO is equal to VOH, so then for the PMOS, if VO equal VOH, which is large, then I will have two quantities, VSG minus magnitude of VT, and I will have VSD. So what is VSD for the PMOS? It is VDD minus VO اللي هي VOH. يعني this is a small quantity لأنه VOH should be close to VDD or equal. And VSG minus VTP, it is equal to مثل ما قلنا VDD minus 0 minus magnitude of VT. So who is larger? This, يعني smaller هو ال VSD, so if the device is going to be in the linear region. Okay, so now to solve for what VOH is, I can set what? To solve for VOH, I can set the following. I can say that K prime IP equals to IN, which is 0, and therefore K prime W by LP times VDD minus magnitude of VT times VSD, which is VDD minus VOH, okay, minus VSD squared over 2, which is VDD minus VOH squared over 2 is equal to 0. What is the value that will give me this quantity 0? If I set VOH to what?
VDD.
VDD. لأنه خلص بصير 0 times VOV and 0 and I get VOH equal VDD. Okay, is this clear? يعني this explains this. Okay, so I get VOH equal to VDD and I can use a PMOS that is grounded. And this way I don't have to use two supplies like was the case in the linear NMOS. هونيك اضطريت إنه أحط two supplies, one of them greater than VDD, which can be costly on chip. Okay. طب هات لنسأل بس سؤال and later we will talk about this. We will introduce different logic families. But let me ask you a question about this. So now what if I have a circuit that has the pseudo NMOS configuration, يعني I have a PMOS here, and then here I have two inputs, A and B, and this is grounded and this is VO. Okay, so what happens here? Let us see. When A and B, and this is V out. If A is 0, what is going to happen? If any one of these is 0, what will happen to VO? IN will be 0 in all of these. So where will the output go? Mean is always on. It will always go to VDD, right? So this will be VDD, VDD, VDD. Except in the last case, in this last case, I will have an RN and VO will be close to VOL. Okay, so technically what we have here is that a circuit, now we reduced, instead of dealing with a CMOS circuit that would have had 2 transistors on top and the 2 transistors on bottom, I only populate the pull down network and I replace the pull up with a pseudo PMOS invert. So يعني pseudo NMOS نحط له PMOS grounded. طيب what are the trade-offs؟ بالسيموس شو كان عندي ال V out؟ بالسيموس كان يطلع عندي VDD 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 or what؟ زيرو صح؟ بالسودو NMOS it will be VDD 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 but I will have a VOL. Okay, I will have a VOL for this circuit. Is that clear؟ طيب okay. طيب let us لكينا see in this scenario I'm going to compare the two inverters. هلا the last type of the inverter is the inverter where I have a CMOS based inverter. Okay, so this is a CMOS based inverter يعني أنا عندي ال VN جاي على ال P وال N and this is V out. Okay, and as opposed to the pseudo NMOS inverter where the P is always grounded and then I have my NMOS transistor with VN connected here. Okay, so for this circuit that is here, okay, when Vn is equal to VDD, I will have N1 in what region? I will have VGS minus VT, the V out will be equal to VOL, and this is the VDS. Okay, so clearly I will be in the linear region and the VDS is small. Okay, and VGS minus VT will be VDD minus VT. And for the PMOS, okay, I will have the device in what region? And the VSG for the PMOS, it will have VSG minus magnitude of VT. This does not change, it's VDD minus 0 minus magnitude of VT minus VOL, right? And then VSD إنه حيكون هو VDD minus VOL, okay? And so this quantity is going to be, which is the larger quantity? عفوا I did a mistake, sorry. هيدي ال VSG is independent of the output in this configuration. It is between S and G. So it is VDD minus 0 minus magnitude of VT and this is VDD minus VOL. Okay, ال VSD. هلا هون we have to have a hint إنه إذا VT مثلا هي around 0.7 volt and VDD is 2.5 and we expect the VOL to be less than 0.2, ساعتها I can clearly say which quantity is larger لأنه هاي حتكون تقريبا 2.5 minus 0.2 and this will be 2.5 minus 0.7 and so this will be smaller and then my device will be in saturated region. Okay, and to solve for VOL I will need to set IP equals to IN. Okay, and IN will be in the linear function of VOL and IP will be in the saturation function of VDD and VT. Okay, so هون بنطلع لها ال VOL from this equation. Okay, now when the input gets connected to both the P and the N, I will get the CMOS implementation. And for this CMOS implementation, if I have Vn equals to VDD, what is going to happen here? if I have Vn equals to VDD, then I will look at the PMOS device, okay, which will have VSG minus magnitude of VT and VSD, and I will look at the NMOS device, which will have VGS minus VT and VDS. Let us see what we populate here in these entries. For the PMOS, this is S, and this is its G, and really Vn equal VDD, so Vn is the G for it. So VSG is VDD minus VDD minus VT, so خلاص هيدا is off, right? And then for the NMOS, Vn is VDD, so this is VDD, هيدا ال Vn هي VDD, so VGS is VDD minus VT, and VGS minus VT, and VDS I want it to be, it will be VOL, right? So what happens if this is off? This means that IN equal IP equals to 0, and what region is the NMOS operating in? بأي region ال NMOS عم يشتغل؟
linear.
بالlinear, right? So this means that I will write K prime W by L times VDD minus VT times VOL minus VOL squared over 2. I want this to be equal to 0. If and only if, what will be VOL? X minus X squared equals 0. شو هي ال X?
0.
0. So the X is going to be 0, so VOL equals to 0. فإذا the CMOS inverter works in a way that when I want to pull up or pull down the output, one of the devices will be off, allowing the other device to force the output fully to 0 or to VDD. ما عم يصير عليها contention from the other device. Okay, this is the basics of the CMOS inverter. Clear? حدا عنده سؤال on this?
Professor,
Yes.
we can go back to the previous type of slide of inverter where you said no, it's independent of V out. إيه هيدي؟
صح.
Yes, I didn't understand why لأنه بالنهاية we have to compare ال VST بال VSG minus VT فكيف هي independent؟
Okay. The ability of the PMOS device to pull up a capacitor or a specific node is independent of the value of this node. يعني خليني أعتبر أنا أنه الأوتبوت بده يطلع من الزيرو ليوصل لعند ال VDD. صح؟ When the output is 0, what is VSG minus VTP for this inverter? For this transistor, sorry. What is VSG minus VTP? VDD minus what? مظبوط? Is it affected by the value of the voltage at this node?
No.
No. So as V out is trying to be charged, طبعا احنا عم نحكي DC هلا so ما نفكر فيها هيك. بس إنه at any possible value of the output, the transistor is on. صح؟ So أنا if Vn is 0, إذا بدي أرجع ألحقها from my perspective, how far can I charge? What is VOH for this guy? If I want to solve for VOH, I'm really just going to say Vn 0, N1 is off, right? Vn 0, VO equal VOH. The PMOS has VSG minus VT, VDD minus 0 minus VT. VSD, VDD minus VOH. I don't know what VOH is. I'm solving for it. But it should be large. Therefore, the delta is small and the device is in the linear region. إذا جيت حطيت IP equal IN I equal 0, حطيت ال current equation لل P in the linear region, okay, it will automatically tell me that VOH equals to VDD without me worrying about what we explained above. Okay, بس أنا what I was trying to explain to you above إنه لما كان عندنا ال NMOS, when I had the NMOS device, it's VGS إذا هيدا ال VO كان VG minus VO, right? So it had a possibility of turning off if VO becomes very close to VG, right? versus in this one VO will not turn إذا صار في بينه وبين ال VG delta of VT لأنه really this is what turns on the channel, right? Here,
regardless if linear or saturation. Yeah.
This is what turns on the channel is VSG, and it is always guaranteed that it is high. So the channel is always on, of course, until VO hits VD, then DS يعني ساعتها I cannot go beyond the supply voltage. So the current will become zero when VOH becomes equal to VDD because it has charged fully. Okay? That's what we meant to say.
Thank you.
Okay, you're welcome. So لكن هلا what we see is that in the complementary, in the CMOS implementation, the devices will not fight with the other one when I'm trying to pull the output up or down. يعني يا أما PMOS is on, it will pull the output up, or the NMOS is on and it will pull the output down. طيب, let me, هلا هون if we have a note about, and then we will go into this with the different regions of the CMOS inverter and specifics. But if we want to assume the unified current model, we will build the same tables, okay? But we need to know for each device what is the VDV set, right? So we will add it to the comparison chart along with VOV and VDS. And we have to give you some assumptions. يعني مثلا assume that VOL will be less than 0.5. Okay, and so if you know that VDV set is 0.7, ساعتها أكيد I'm going to have, and this happens to be مثلا 2.5 minus 0.2, أكيد أنا I know and when I'm solving for this that this will be the winner and that I will be operating with my VDS effective equal VDS. So if we solve any example using this, we have to be very clear on what the assumptions of the result will be for you to be able to solve using the unified current model. يعني حيكون كتير simple مثل ال long channel equation. هلا طبعا for the PMOS you're going to use VSG, VSD and the absolute values, okay, of all of these parameters. هلا what does it mean to us بس graphically هيك out of يعني بس to emphasize when I have a resistor based inverter, so the load is the resistor, this is VDD, and this is my inverter, and I'm operating it with some Vin and I get some V out, and I really want to see where does the solution work. لأنه أنا I know if I have a transistor with some VG applied here, هلا هون عندنا نحن VGS equal to Vn. Okay, so هيدي as VGS increases, the Vn increases. And if I have a VDS here, and here VO equals to VDS, but here I am controlled, I have to follow also the behavior of the resistor. So if I had this standalone, then I know that the ID VDS characteristics follow this graph. يعني I will start in linear and then saturate, and VGS increases, I have a higher current, so on, so forth. So when I implement the linear resistor, okay, what is the equation of the current for the resistor? So هيدا ال R اللي هون, this R which is sitting here, it has an equation. So this is IDN. This is IDN part. Let me write it in a different color. This is IDN. هيدي للNMOS. Okay. Okay. And then I have here the IR. كيف شكله ال IR? What is the equation for IR? It's VDD minus what? Minus VO, which is the VDS over what? Over R, right? Type. So it is VDD minus VO over R هي current, right? Okay, اللي هي VDS. Great. طيب هيك لنشوف, can I draw it on top of this? ما هي VDS عندي إياها هون. I want to draw IR. So when VDS equal to 0, what is the value of IR? VDD over R, right? And then when VDS equals to VDD, what is the value of IR? 0. صح? When VDS equal to VDD, the IR راح تطلع 0. So really the current of the resistor walks over this line. Okay? يعني So at any VDD value or VO value, I can calculate the current and it should fall on this line. Let me ask you a question. When VGS equal to 1, when Vn equal to 1, what is the solution of VO? When Vn equals to 1, يعني أنا الترانزستور اللي إلي is following this curve here, right? When Vn equals to 1, this is the current characteristic. Where is the solution? How do I solve for VO? I solve for VO when IR equals to IN. يعني at what point? At the intersection, right? At the intersection, right, Hisham? Thank you. Great. Type when Vn equals to VDD, where is the intersection? Can it reach VDS equal to 0? Can it reach VDS equal to 0? When Vn equal VDD, هيدا الكيرف. هيدا Vn equal 2.5 equal VDD. Where do they intersect? They intersect at a point here, which is what? Which is my VOL. Okay, so this is just a graphical interpretation as to why VOL cannot reach 0. لأنه really I'm looking for the location where the two current characteristics meet. And in reality, it is because the resistor is always on and the device is on at Vn equal VDD, so I have a voltage divider circuit. Okay, وضحت وين ال VOL على هيدا الجراف. هلا why would I benefit from such a graph? I benefit from such a graph لأنه أنا I know إنه what if مثلا I have another resistor and this other resistor, what if the resistor R increase? ساعتها شو بصير بهالpoint VDD على R? It will drop لأنه أنا I'm dividing by this R, right? So where will the line be? Like this. What happens to my VOL? It becomes lower. Okay, so just the basic notion إنه أنا بعرف يعني what we really want to know from this, and I'm going to draw it clearly on another slide. What we really want to know from this is the following, that when I draw the resistor current versus VDS, so this is IR versus VDS, we want to know that it intersects here at VDD, okay, and here it intersects at VDD over R, okay, and if I have another R that drops, then or that أخذناها R كبرت صح? So if I have another R that increases, then I can say that really VDD over R is going to drop and the line is going to be this one, and therefore if I have this as the current characteristic when Vn equal to VDD for the NMOS, then I will end up having here a VOL1 and I will end up having the intersection here as a VOL2. Okay, so just a trend, يعني more like the intersection of a line with a curve, what will happen to it. حدا عنده سؤال? Anybody has any question? Well, yes, I mean, depending on the technology, if I increase R, if I can have a very large resistor, what is going to happen? Who in real life, you have R here, and then you have, oh, pardon me, then you have the NMOS device, you have a resistor here, and you have the NMOS device acting as some resistor Rn, right? When Vn is VDD. Okay, and so what is VOL? إذا بدي أفكر فيها للNMOS device هو Rn على Rn plus R. So what happens whenever R increases? What happens to this whole quantity? It's going to drop. Okay? Clear? حدا عنده سؤال؟ Okay. طيب great. طيب, so now we're going to look at the Now we're going to look at the other parts of the lecture. So هلا هيدول النوتس على how a PMOS interacts with an NMOS. I don't want them. We're gonna skip these slides up to slide 47. So I will write a note on the Moodle for you. And now the question becomes, well, if I am solving for the different points for the CMOS inverter, اللي هو PMOS and NMOS, and both are connected to the same Vn, and I have Vout, and this is Vn here. What are the different regions of operation that I care to use when solving for the different quantities VOL, VOH, or VIH, or VIL? So let us see. خلينا نطلع على output. Okay, so one rule of thumb in this circuit to try to see how to solve for it is that when I start with VO high, then this is large, okay, and the VDD minus VO for the PMOS is really small, okay. This is very important for us to remember. يعني if both devices are on, then we want to look for the NMOS device, and for the PMOS device, what are their specific VSD and VDS. So let us look at this slide here, and let me erase this one. Okay, so let us look at this slide here. So the NMOS will have VGS minus VT equal to VN minus VT، لأنه هيدي حأرسمها أنا هلا again. Okay, so this is Vn, okay, and this is Vout, okay, and the PMOS will have VSG minus VTP and VSD equal to VDD minus Vn minus VT, and the VSD للPMOS هي VDD minus Vout. And now as I walk in the different regions, okay, يعني مثلا to solve for VOH, I'm going to set Vn to 0, so this guy will be off, and this will be VOH. So for the PMOS, what will this be? This will be VDD minus VT, and this will be VDD minus Vout, and I can then find what the region is, okay, which is minus VOH اللي هي حليناها قبل وقلنا إنه هيدا حيكون بالlinear region. So as you see here, they're telling you that the PMOS is in the resistive and the NMOS is off. Okay. هلا as I move down in the curve, let us see what would happen. Okay, so if I move down in the curve, let us say I want to solve for VIL, which is here on the verge of turning on. Okay, the output is still high, so if I have Vn equal to VIL, okay, then the Vout will be really VOH. It's slightly smaller than VOH, so I will just plug in. So for the NMOS I have VIL, which is greater than VT, but it is small, so هيدي automatically أنا بجي برسم على الNMOS إنه this is small. And then the output is going to be VOUTH, which is large. So automatically I'm going to draw here that this is large. So who is smaller? The smaller triangle. Therefore, I expect this to be in what region? To be in the saturation region. Okay. What about the PMOS? For the PMOS, what I have here is this is VDD minus VIL minus VT, okay, and VIL is a small and absolute value, of course, and this is VDD minus VOH. So for the PMOS, this is a small, and VOH is large, so VDD minus VOH is going to be small, and the chances are, since VIL is small and VDD is large enough, that this is big. So you can start to see that these are complementary. Okay, يعني a small output here corresponds to a small VSD here corresponds to a large VDS here, and in a similar fashion, a small VGS here corresponds to a large or VOV to a large VOV on the PMOS. So I would expect this to be small, and I would expect this to be in the linear region, and we can follow whatever is explained to us here on this slide. Okay, so is this clear? حدا عنده سؤال؟ Okay, so things are complementary. هلا بس نوصل للmain intersection point where Vin equal V out, then chances are the two are going to be in saturation. And next time we're going to talk about the PMOS being off, and we will conclude this section here. Okay, so I want to make it just clear once for all, and where does the PMOS turn off and the different regions of operation. اوكي بس as you notice here انه الانموس حيبلش off حيبلش بالسات لانه the output is high لانه it has a large output, and then it will turn to linear when it turns on strongly and it pulls the output down to low, to zero. Okay, so the anmos ببلش يصير linear على when it's pulling down strongly, and the PMOS is linear when it is pulling up strongly. We will see when the PMOS turns off and summarize this section next time. Right, thank you everybody and have a good weekend. Yeah, take care.
Professor?
Yes, yes. Thank you.
In the pseudo-NMOS implementation, why is VOL assumed to be low if we have a resistance above the output node and we have the resistance below? Like, why did we assume the voltage division over the resistances to be low?
Okay, لأنه الترانزستور it will have a small resistor value. يعني if you recall in the beginnings where we studied, let me just go back to the slide. If you recall in the beginnings, here talking about this, huh? Typically,
Sure.
this one, you're talking about this, right? Can you hear
yeah,
me?
but I mean when the top one is also a PMOS transistor whose gate is grounded.
هيدي okay, because we designed the PMOS, to have so that the resistance ratio, okay, يعني أنا if I'm solving for VOL, right, which will give me Rn over Rn plus Rp, we design it, the ratio of the two transistors such that when this is on, to have it closer to zero. Okay, يعني هو بيكون bulky, it is slow, it has a large RP. Okay, so it will pull things up slowly. So anytime a pull down path competes with it, it will pull things much faster. حيكون عنده low resistance وحيوصلني على ground. يعني this is just, we refer to this like it's a keeper device to keep the high level. ما ضروري يكون strong and have low resistance. Okay. So تكون small device. هي is a small W by L يعني عندها large resistance.
Okay, thank you.
Okay, thank you, Mario. Okay, anybody has any other questions? Which red dot, George?
In the last graph, we were looking at the one with the different regions of operations.
So in those different regions of operation, what are they signifying here? Here they are signifying that if the input is 0, the output is 2.5. This point here is when my input reaches VT, after which the NMOS will start to turn on. Okay, so هنحكي عن whole regions. We will talk about these breakpoints vertically, what they are next time. Okay, on Monday. Okay. لأنه هون في مقابلة أنت ال PMOS turns on كمان.